previous video, we looked at how flat surfaces behave when there is pressure mounted on top of them. Let's use this session to look at how curved surfaces are affected by the pressure of liquids when they are submerged in those liquids. In the previous session, we talked about hydrostatic force always acting perpendicular to the surface of the contact. The situation is the same for a curved surface also. However, if we want to get a perpendicular line to a curved surface, we need to draw a straight line from the center to that curved surface. Because we know pressure at the top is lower than pressure at the bottom, F1, F2, F3, F4 and then F5 will have different magnitudes, which is shown in the length of their lines of action. Now, if we look closely at the forces that we've drawn, we can resolve each one into their horizontal and vertical components, so that after resolving, we can work with all the x components of the forces and then all the y components of those forces. When we put all the horizontal forces together, we can have one Fh, which is the horizontal component of the resultant force of all the forces that are on the curved surface. And then we can also have Fv, which is the vertical component of the resultant force, which is coming from all the vertical components of the individual forces. Now let's go back to the notes and then see how to deal with curved surfaces and how to solve questions on curved surfaces. To determine the hydrostatic forces on curved surfaces, we do the following. The first one is to project the curve onto a vertical plane. Once you have been able to project that surface onto a vertical plane, it behaves like a flat surface that is vertical. And we can use the formula that we studied for vertical surfaces, which says that the horizontal force or the resultant force is equal to the specific weight times y bar times sine 90 times the area. Then step 3. we need to determine the real or imaginary volume above the curve. So we'll explain what real or imaginary volume means in this context. So let's use a simple one. We know volume equals length times breadth times height, and length times breadth is area. Therefore, the volume can be said to be the area times the depth of the fluid. Now, the important part that we are supposed to remember is that the real or imaginary volume should be above the curve. We must also note that if we want to determine the vertical force on the curve, then that is just the weight of the fluid that is on the curve. So the weight of the fluid we can determine from the specific weight formula, where specific weight equals weight over volume. So we can say that the weight is just the specific weight times the volume. So once we are able to get the volume above the curve, then we can get the vertical force, which will just be the volume times the specific weight of that particular liquid. Once we have been able to determine the horizontal force and the vertical force, then we can use the magnitude and then the directions of those forces to determine the resultant force and the center of pressure. So in this particular situation, we saw that the horizontal force is pushing the curve to the right, and the vertical force is pushing the curve to the bottom. So the resultant force will be somewhere in between them, and we can determine this resultant force by just using Pythagoras' theorem. Then also for curved surfaces, the center of pressure is the angle at which the resultant force meets that curve. So let's explain further what the real or imaginary volume above the curve means. Let's use these two examples to look at the real and imaginary volume. So in our first situation, this is the curve that is submerged in the liquid. And the volume above the curve is not actually in the liquid, but it is an imaginary volume that is above the curve. In the second situation, we can divide the curve into two such that we have one that is on top and then one that is below. For curve 1, the volume above the curve is a real volume, that is the volume of water that is sitting above that curve. However, for curve 2, the volume above the curve is an imaginary one. So it is imaginary because there is no liquid in there. We still continue with our convention that we need the volume above the curve to get the vertical component of the resultant force. So let's use this example to explain what we've been talking about so far. We are supposed to determine the resultant force on an object in the direction of this force if there is a radius of 1 meter and the liquid has a depth of 2 meters. So before we start, let's determine the number of curves that we have. Then from the steps that we've talked about, we need to project each curve onto a vertical plane and solve for the horizontal forces. And don't forget how to determine your Y bar. Then the next step is to determine the volume above each curve, and that will help us to determine the vertical forces. So above curve 1, there is a small volume of water, which is a real volume. To get that volume, all that we do is to determine the area of the square and then subtract the area of the quarter circle, and we multiply that by the depth of the object. Then after doing that, we can determine the vertical force on that curve. We do the same thing for the two other curves, and one thing we are supposed to note is the direction of that vertical force. Then after getting those two forces, that is the horizontal force and the vertical force, we use that to determine the resultant force by just using Pythagoras to get the magnitude, and we can use trigonometry to get the angle that this resultant force makes with the curve.